Study Unit 3, Lecture 2. This lecture continues with switch characteristics and classification of switching types. So for switch characteristics, there are four categories where the ideal switch is preferred to operate. These categories are when the switch is off, so the off state, the switch would ideally be open. In the on state, the switch would ideally be a short circuit. During switching, the switch will switch as fast as possible. And finally, the thermal and mechanical characteristics of the switch must be such that the switch is very well suited for longevity in any design. So ideally a switch in the off state will have a low temperature independent leakage current. Low leakage currents means low power loss. Additionally, when the leakage currents are very low, it makes it very easy to put switches in series. A good switch will have a high forward and high reverse voltage blocking ratings. What this means is that when the switch is off, it is able to withstand very high forward and reverse voltages across the terminals of the switch. By having high forward and reverse voltage blockage ratings, it makes it easier to design since switches will no longer have to be put in series. The reason this is important is that if a very high voltage blocking is required, then switches will oftentimes be put in series because the voltage blocking of each switch will be cumulative when all the switches are considered together. The switch should have a high static off-state avalanche capability. What this means in short is that the switch is able to absorb transient overvoltage stresses which occur when the switch switches. The switch should also have a high static and reapplied voltage transient capability. What this means is that the switch should be able to withstand having very high voltages across the terminals without the switch being on. This essentially means that a very high voltage can be applied across the switch while it's open and there will not be a false turn on. A good switch in the on state will have a low on state conducting voltage or low on state conducting resistance. Essentially what this means is that when the switch is on, there is a very small voltage drop across the terminals of the switch, and if the switch has very low resistance, then there will be minimal power loss through the switch as it conducts current. A good switch will also have a high on-state current density capability. What this means is that the switch is able to have very dense currents route through the switch without additional thermal heating in the switch. In other words, if the switch is able to conduct a large amount of current, then it means that switches do not need to be used in parallel to conduct large amounts of currents. It also makes the thermal design much easier because if the switch is able to conduct very high current levels, then the amount of heat dissipated in the switch will be low. Finally, when the switch is in the on state, it should have a safe off from short circuit condition. In other words, if there is a short circuit condition, then the switch should switch off in a safe manner. When it comes to switching, the amount of power which is needed to actually control the switch should be quite low. The shorter the switch times, the better, especially if these switch times are independent. This makes the switch behavior predictable. Switches which switch quickly also minimize the power loss during the switching process. The switch should also have a high current transient capability in order to handle the inrush current which will inevitably pass through the switch. A good switch will also have a high surge current capability. What this means is that the switch will be able to handle high current transients which are caused by faults elsewhere in the system. This is useful because it will prevent the switch from tripping unnecessarily because of a fault elsewhere. Finally, to handle aspects such as the inrush mentioned in the previous lecture, the switch should have a large safe operating area. The larger the safe operating area, the more reliably the switch can be used. From a thermal mechanical point of view, the switch should be easy to connect and easy to mount and integrate with other parts in the system. A good switch will be mechanically, electrically, and thermally robust, with very little drift as the switch changes mechanically under different electrical conditions and under different thermal conditions. The switch should have a matching substrate structure to minimize stresses. What this simply means is that the switch should have a good internal structure so that the stresses between substrates are not significant. Finally, the ideal switch will have an infinite lifetime and never degrade over time. The process of a switch turning on and then off again is called a commutation. Depending on how the switch commutates, there will be 4 different switching classifications. These are hard switching, soft switching, resonant switching, and finally naturally commutated switches. These switching classifications are determined by the switching time Ts and the commutation time Tq. The commutation time will always be less or equal to the switching time. This diagram from the reference text, figure 6.11, shows the 4 different switching classifications. So, in hard switching, the commutation time is equal to the switching time. In soft switching, the commutation time is less than the switching time. In resonance switching, the commutation time is also less than the switching time. And in the naturally commutated switching state, the commutation time is 0. The commutation time is defined as the time it takes a switch to reach a 0 current at turn off or to reach 0 volts at turn on. A more intuitive way to think of commutation time, it is a period during the switching process in which switching losses occur. So using these definitions, hard switching is when the switching losses occur over the entire switching period. In soft switching, the switching losses are over before the switch has reached its steady state. What this means is that as the switch switches, all the losses will occur in a short period, but will be over before the switch has actually completed the entire switching process. During resonance switching, the commutation time is much less than the switching time. This is achieved by effectively unloading the switch by diverting the currents or voltages away from the switch while it switches. This means is that as the switch completes its switching, it does not actually see the load that it is switching to. Switching the voltage across a switch when the current through the switch is 0 is called zero current resonant switching. In naturally commutated switching, the commutation time is 0. This means is that both the voltage across a switch and the current through the switch are 0 when switching occurs. In naturally commutated switching, the switching losses are virtually 0. And this concludes lecture 2.